Imagine a city where nobody has a blueprint, nobody gives orders, and nobody understands the whole plan. Yet thousands of workers still build, hunt, defend, repair, and evacuate when conditions turn dangerous. They pull living walls into place, form bridges with their own bodies, patrol highways in the sky, move their young between shelters, and defend borders that can shift with a single broken branch. That city is not underground, and it is not built by humans. It hangs inside tropical tree canopies, where every road can sway in the wind, and every home can be hammered by rain. Its builders are weaver ants, and their strangest construction tool is not a machine or even an adult body part, but their own larvae. The stakes are bigger than nest building, because the same colony also has to feed hundreds of thousands of members, repel rivals, protect brood, and survive storms without any ant seeing the entire system. So how does a society with no foreman become an engineering crew, hunting network, nursery, border force, and emergency response system all at once? For an American viewer, one detail matters immediately. These are not the familiar ants crossing a kitchen counter in Ohio or Texas. Asian weaver ants, Oecophila smaragdina, range across tropical Asia into northern Australia, while Oecophila longinota lives in parts of tropical Africa. Different species, same remarkable lifestyle, life above the ground. That aerial life changes the problem of being an ant. A ground-dwelling ant can vanish into soil cracks. A weaver ant lives on leaves and branches that bend, shake, heat up, tear, and get hammered by rain. Every route is narrow. Every bridge can move. Their answer is not one indestructible nest. It is a colony that behaves like a distributed network. Start with one worker. Like other ants, it has a head, middle body section, narrow waist, abdomen, 6 legs, and 2 antennae. Long legs help it race across branches and leaves. Hooked feet and adhesive structures help it hold on. Larger workers carry strong mandibles for pulling, fighting, and restraining prey. Those mandibles matter because weaver ants do not rely on a functional sting. Their defense is built around biting, gripping, chemical communication, and coordinated attack. The colony's real weapon is not the bite of one ant. It is how quickly one ant can bring others. The antennae are constantly sampling the world. A worker that finds food, danger, or useful territory can trigger recruitment through chemical signals and behavior. Nestmates arrive. A discovery made by one body becomes a colony-level response. Now look at the nest. It does not begin as a pile of dirt or a hollow dug into wood. It begins with living leaves. Workers choose flexible foliage and pull leaf edges toward one another. If the gap is too wide, they can form chains with their own bodies. One ant grips another, then more join, until the chain acts like a living cable. Once workers pull separate leaf edges close enough, they need to fasten them. Adult weaver ants cannot spin the silk required for the job. Their larvae can. So workers gently pick up mature larvae in their mandibles and carry them from one contact point to another, like living silk dispensers. A worker touches a larva to one leaf surface, then another. The larva releases silk. Fine threads bind the leaves together. More workers repeat the process until the connection holds. Their silk helps create the nest itself. In a literal mechanical sense, the colony builds part of its home with its own nursery. And one leaf nest is rarely the whole story. Mature weaver ant colonies can occupy many nests spread across one tree or several neighboring trees. This arrangement is called polygamy. One colony, multiple nest sites. Instead of placing every worker, larva, food reserve, and reproductive asset behind one entrance, the colony distributes itself across the canopy. That changes what home means. Home is not one leaf bundle, but a connected territory. Some nests hold more brood, others more workers. In a mature colony, the queen is typically associated with a central or main nest, while traffic moves between sites along branches and stems. Large colonies can reach hundreds of thousands of ants. Yet the queen is not a manager issuing daily orders. She matters because she produces eggs, not because she schedules patrols. Workers respond to local cues. Food appears, recruitment follows. A useful leaf gap appears. Workers begin pulling. An intruder arrives. Defenders gather. Many simple decisions, repeated across thousands of bodies, create behavior that looks coordinated from the outside. The colony can look centrally controlled precisely because no individual has to control every detail. The workforce is not completely uniform either. Weaver ant colonies include smaller and larger workers with different tendencies. Smaller workers often spend more time around brood and internal nest tasks. Larger workers are more prominent in risky outside jobs, such as foraging, hunting, territorial defense, and construction. It is not a rigid corporate chart. Body size, age, location, signals, and immediate need all help shape what happens next. Food shows the same logic. Weaver ants hunt insects and other small arthropods. Prey that is too difficult for one worker can be seized by several, pulled from different directions, and immobilized through collective force. The useful unit is often the group that forms around the problem. But prey is only part of the diet. Weaver ants also collect sugary liquids, including honeydew, made by sap-feeding insects. That creates an unusual partnership. Ants may protect honeydew producers while harvesting their carbohydrate-rich secretions. Protein-rich prey helps support growing brood, while sugars help fuel active workers moving through the canopy. Their patrols can reduce some insect pests, and humans have used that behavior for centuries in parts of Asia, including in citrus orchards. Think of it as pest control, supplied by a standing army that lives in the crop and largely feeds itself. Of course, territory brings conflict. Rival ant colonies compete for canopy space. Birds, spiders, and other predators can disrupt activity. Even another colony of the same weaver ant species may be treated as hostile. Territory is chemical as well as physical. Workers recognize colony-associated odors, and unfamiliar ants crossing a defended boundary can trigger aggression and recruitment. To us, a branch may look empty. To the ants, it carries information about routes, food, territory, and danger. A fight is rarely elegant. Ants bite, grip, pull, surround, and try to overpower opponents. Numbers matter. Position matters. The speed of recruitment matters. A lone worker can be overwhelmed quickly. A worker connected to thousands of nestmates is part of something far larger. The dramatic unit is not the ant, it is the network. That same principle becomes even more important when the enemy is weather. Tropical trees face heavy rain, strong wind, falling branches, and sudden shifts in temperature and humidity. A nest made from leaves looks fragile because it is fragile. Severe weather can damage nests and kill ants. Weaver ants are not protected by some invisible force field just because they cooperate. What they do have is behavioral flexibility. During rainy periods, foraging can drop noticeably. Instead of keeping normal traffic exposed on wet branches, workers reduce outside movement. Once conditions improve, activity can recover. A worker crossing a wet branch faces poor traction, raindrop impacts, and a greater chance of being knocked away. If the colony can wait inside shelter, forcing business as usual may cost more than it gains. Sometimes the smart collective move is not to work harder. It is to stop exposing workers to a bad route. The nests provide some protection. Overlapping living leaves create enclosed spaces reinforced with silk. They are shelters, not storm bunkers. Strong wind can still tear them apart, but a colony spread across many nests does not depend on one structure. When local damage occurs, workers can use the same basic weaving behavior that built the nest in the first place. Leaves can be pulled back into useful positions and reinforced with fresh larval silk. Damaged nests can also be abandoned and replaced over time. Their architecture is not a finished monument. It is an ongoing maintenance process. Researchers have also observed weaver ants using protected artificial nesting spaces during stormy seasons. That does not mean the ants understand a weather forecast or predict a cyclone. It means local conditions can make one shelter more useful than another, and worker behavior can shift accordingly. Their resilience comes less from prediction than from having many ways to respond. Now comes an important distinction, because this is where ant stories are often blended together. Some ants are famous for surviving floods by linking their bodies into floating rafts. Fire ants in the American South are the best-known example. It is tempting to give weaver ants the same ability because ants survive floods sounds like one universal trick, but that would be misleading. Weaver ants are canopy specialists. Their first advantage against ordinary ground flooding is already built into where they live, above it. Colonies in flood-prone tropical habitats can occupy vegetation that remains elevated while water rises below. Leaf nests keep brood away from the forest floor. If water physically tears workers from vegetation, individual ants may struggle, cling to floating material, or be lost. But the giant organized rafting behavior associated with fire ants is not the defining flood strategy of Oecophila. Different ants evolved around different environmental problems. Biology gets more interesting when we stop handing every species the same superpower. So when rain becomes dangerous, weaver ants can reduce exposed activity. When wind threatens, grip and enclosed leaf chambers matter. When a nest is damaged, repair or relocation becomes possible. When water rises below, canopy living provides elevation. None of those responses is magical by itself. Together, they make the colony harder to erase with one local disaster. Another advantage is already built into daily life. Workers routinely move between nests, carry brood, and use established branch routes. A multi-nest colony does not need to invent transportation only after something goes wrong. The queen is the difficult passenger because she is a major reproductive asset. Moving her is risky. During nest relocation, workers can surround and protect her while the colony shifts position. Once again, survival depends less on a heroic individual than on maintaining a functioning network around a vulnerable part of the system. And that brings us back to the question from the beginning. How can a colony with no foreman build, hunt, defend, raise young, and respond to disruption? Not because each ant is secretly calculating the whole plan. It is because each ant can perform a limited set of useful actions, detect local cues, communicate, and recruit others. Pull, grip, carry, bite, follow, signal, repair, repeat. When thousands of workers do that in the right context, complexity appears at the colony level. There are limits. A severe cyclone can destroy branches faster than ants can repair them. A colony can lose nests, brood, workers, or its queen. Cooperation does not make the environment harmless, and distributed organization does not guarantee survival. It changes the odds. But those odds are impressive. A creature only millimeters long can become part of a society spanning entire trees. Larvae become silk dispensers. Workers become living ropes. Scent becomes information infrastructure. Leaves become rooms. Branches become roads. Many nests become one home. A weaver ant colony can function as architecture, communication system, hunting team, nursery, border patrol, and disaster response network at the same time. The payoff is not that weaver ants are tiny humans. They are not. Their power comes from solving problems in a completely different way. No ant needs a map of the whole colony. No worker needs to understand the final structure. Evolution has connected simple actions into a system that can build, adapt, and recover. A storm can tear open their house. Rain can shut down their roads. An enemy can cross their border. Water can erase a route in seconds. Yet the colony does not wait for one brilliant ant to save everyone. It needs workers that grip, signal, carry, recruit, repair, and respond. One weaver ant is small enough to disappear beneath your fingertip. Thousands acting together can turn a trembling tree into a functioning city.